Okay, so it appears that what we showed up here is that the classically, if you consider everything in a completely classical way, that the momentum is invariant um, when you boost from one inertial reference frame to another. Okay, but the thing that we've left out here is that we know that the classical velocity transformation is incorrect, right? We've discussed, we know now how to actually correctly and generally transform velocities from one reference frame to another using the Lorentz transforms. So let's use the Lorentz transforms and see what happens. Okay, so now I've written down um, the uh, the new initial momentum for the two particles, the one that was right moving in the unboosted frame, the S frame, and the one that was left moving in the S frame, and where now you see that we have the correct Lorentz transformed velocity. So the right one is now the one that was right moving in the S frame is u minus, the velocity now is u minus v divided by 1 minus uv over c squared. If you go back to the notes where we did the Lorentz velocity transformation, you'll see that's correct. And the one that was left moving in the S frame is now minus u minus v divided by 1 plus uv over c squared. Okay, now we can rewrite this like this, and here we see that we have this numerator which is similar to what we had in the purely classical case. Okay, but now we have this denominator, and the key thing here is that this cannot be written as the initial momentum in the unprimed frame plus a constant. It can't be rewritten that way. Okay, so what this means, and this is completely general, if you also wrote the expression for p final prime, the final momentum in the final momentum in the primed frame, you'd find something very similar, but the same thing holds. You can't write this expression in terms of the initial momentum. I mean the momentum in the unprimed frame plus a constant. Okay, so what that means is that this classical momentum m times v. Okay, so what we've assumed here is that the classical momentum is equal to mv. Okay, so again, the classical momentum for a particle of mass m and speed u is just m times u. So apparently we have two choices. Okay, we can abandon the notion of conservation momentum, or we can redefine what a generalized momentum is. We can redefine momentum. Apparently, if we decide not to abandon conservation momentum, and I think that would be a bad thing to do, then we need to redefine what momentum is. Okay, so we need a different expression for momentum. Okay, so again, we have two choices. We can either abandon the conservation of momentum, or we can redefine momentum. And obviously, what we're going to try to do is to find an expression for a generalized momentum which is invariant between coordinate systems that are moving with respect to each other.